Okay. So, hi everybody. My name is Michał Dominiak. I work at NVIDIA for about a year now. And one of the principal things that I work on is Thrust, which is a C++ parallel programming library that provides you a lot of algorithms that are modeled after how the STL looked like, but allow you to, in a mostly invisible to you way, run them on our GPUs or on other runtimes that we support. But algorithms aren't the only things that we provide. There's a few more things, and one of them is what this talk is about. So memory resources. So some time ago, this was pretty much my first big thing that I did on the project when I joined NVIDIA. Okay, so a bit of background information just to catch everybody up to speed. And if you have a question or I skipped over something and you are not following what I'm saying, please interrupt me because there's like layers of what I'm going to talk about, and it would be good if everybody understood every layer because it's going to get worse if you miss something. So just raise your hand if you don't get some part. All right, so let's talk about allocators. How many of you have ever used allocators? Okay, of those who didn't raise their hands, how many of you wrote a line of code that looks something like this? I think we have a total number of people being equal to the total number of hands raised. Good. So, do you want to revise your previous answers? Okay, so this is how a vector looks like, right? Roughly, with some amount of code under the three dots. It's not significant here. So we have a default template parameter, which is defaulted to CUDA Allocator of t. So the first declaration here is mostly equivalent to just writing this, right? Okay. So how do we actually use this? Because vector uses allocators to allocate memory, sure, but what's the API that it uses to actually allocate memory? So first of all, we have to have an object of the type that is an allocator. We'll use CUDA Allocator because that's provided. Then you can allocate one object of a given type for which the allocator is created for. In this case, we will allocate memory. This does not construct an object. This only allocates memory for a single stud string and gives you a pointer back. Then we are supposed to use the member function of the allocator called construct to actually construct an object in this place in memory that was allocated from the allocator. By the way, and note the subtitle there. And by the way, every single allocator has to provide this member function, even though pretty much always this will be placement new. Then we can print the string, and by the way, we are constructing the world's worst hello world that we could possibly construct, because if your implementation of the standard library cannot fit hello world null byte inside a small buffer of stud string, then you are also going to use allocators inside that construct. Then we are supposed to use the member function of allocator called destroy to actually call the destructor of the object. And by the way, every single allocator has to define this function. And by the way, pretty much always, this function will amount to an explicit destructor call. And then we can deallocate, and this is pretty reasonable. So, as I said, this is the world's worst hello world. We can make it worse. We can do formatting like this. Who knows what's coming? Good. That figures. So we are still pre-C++ 11. That is going to change on the next slide because we are going to use C++ 11. C++ 11 gives us this beautiful mechanism called allocator traits that provides default implementations, provides sensible defaults for some member functions and some member type defs of allocators that were previously required to be specialized every time inside a class definition. But now the way we use allocators is different and more complicated because every single thing that we access about the allocator, we are supposed to access through allocator traits. Users are not supposed to specialize allocator traits because they are supposed to always give you defaults and you are supposed to override them by defining stuff inside your allocator. But as many discussions on the library working group in the committee have proven, we cannot discount people who specialize allocator traits, which is sometimes sad. But now, your allocator only has to define what allocate means and what deallocate means, because obviously, because you're supposed to provide some way of allocating deallocating memory, but the construction and the destruction is provided by allocator traits by default. So it's nicer for authors of allocators. It's so much worse for users of allocators, though. So what is separation of concerns? Because we've seen the allocators do many things on those slides already. They allocate the memory. OK, this scans. That makes sense. It's an allocator. It's supposed to allocate memory. It deallocates memory. That's obvious. Once you allocate memory, they are supposed to also know how to deallocate it. But it also constructs objects for some reason. Like, destroying objects once you start constructing them is also reasonable, but why? Why in the world would we do this? So here's a bit of historical trivia from an interview with Alex Stepanov, the author of the STL, from March 1995, by the way, which means I was about a year and a half old at that point. It's old stuff. People wanted the library to provide some mechanism for abstracting memory models. We invented a mechanism called Allocator, which encapsulates information about the memory model. And then he drops some phrases like T star and T huge star. I'm surprised that there wasn't like T far star just to trigger some additional people. But he also mentions that not all of those pointer types are going to use size t for sizes and pointer diff t for differences between pointers, which was the assumption of the STL prior to this point. So in essence, the original motivation for this mechanism wasn't to tell you how to allocate memory. It was to be able to interact with different memory models and different kinds of pointers and different kinds of references. In fun fact, currently the standard requires that every of those places that say I have a member type def that is reference, that always has to be value type ref. You are never allowed to provide any reference that is not the built-in reference to the value type of the allocator or of the container or of anything else in this ecosystem. Another fun fact, Thrust actually preserves this because we have different pointers for different kinds of backends that we allocate memory for, and we actually have different reference types because sometimes we want to transfer memory from one place in the system to the other. We'll get back to that. So going from allocators and trying to separate the different layers that we are operating on, because we have the layer where we allocate memory, and we have the layer where we care about object lifetimes and the means of their constructions and so on. So let's try to write a simple C++11 Malloc allocator. It's going to have a value type def to say what it allocates. It's going to have an allocate function, which is going to take the number of elements to allocate. And it's going to invoke some mechanism for allocating memory. In this case, this would be Malloc. And by the way, on this slide, this size of is the only place where we actually need t. And for deallocate, we don't even care about the count. We just call free, because that's how the API looks like. So there's a singular place in this code where we care about what t is. And we only care about a value, which is going to be a constant, but is a value that isn't multiplied by a runtime value. So this doesn't actually give us anything. And when we use this allocator for many different types, we are going to instantiate all of those calls for every single type for which we instantiate the allocator. That's a lot of code. So let's try to do something different. For multiple reasons, though. This is the only way in which you can, like this or a shared pointer or some other kind of a pointer that gives you essentially reference semantics, is the only way that you can possibly write a caching allocator that actually conforms to the requirements for an allocator per the standard. Because allocators have to be copyable, and after you copy them, you have to get back an equivalent allocator, which means that when you allocate memory on the original one, you have to be able to deallocate it to the copy, and vice versa. So you have to have some place where you reference something. But once you have this, you just write an allocate function, which again makes use of size of t, but doesn't actually implement the allocation. It defers to something else that doesn't actually care about t. And then when you deallocate, you mostly do the same. And by the way, in this case, I'm also going to tell the pool how big this allocation was, because I have that knowledge. So I can greatly improve the performance of the memory pool by telling it everything it may need to know to actually look into the right places. And this starts to look very familiar for those who know C++ 17 a bit, right? Because we can just go from, we can just go from a memory pool to a memory resource, which is a more abstract idea. It's an interface for doing exactly this, for allocating memory and deallocating memory. And we also make use of the alignment of T, because alignment is important when allocating memory. But other than that, we've arrived at the idea of StudPMR. Arthur Adwire had this talk last year at least 2 conferences that I know of. The title of the talk was "An allocator is a handle to a heap." So we have the resource allocator is obviously the allocator. The memory resource is the, quotes, heap that we get memory from. And this is a very nice model for like, just this statement is a very nice model for thinking about this. Okay, so let's quickly go through the shape of what the StudPMR memory resource is. It's a class that has some public members. It has allocate, which gives you back a Voidstar, so it gives you back a pointer to some memory. Takes the number of bytes that you want, takes the alignment that is defaulted to align of max align t. Max align t, by the way, it has got to be the worst name in the standard. You also have deallocate, which takes the pointer that was allocated from allocate. It requires you to give it the same information you've given previously, so the sizes have to match and the alignments have to match. Then you have a function that tells you whether 2 memory resources are equal. And since this is meant as a base class, this is the only reasonable way to actually compare those. And then you have the private guts, where you have the actual virtual functions that you are supposed to override in actual implementations of memory resources. They have exactly the same signatures as the things above, only they are virtual and purely so, and have the do underscore prefix. And I'm just realizing that my is equal is not const no except qualified, but it should be. All right, makes sense so far? All right, let's talk about stateful allocators, because suddenly our allocator has a pointer that we have to copy around, which means it has a state. we can have two different allocators of this type that are not equal because they do not point to the same underlying memory resource. We had a problem in 03 and 98 because containers were allowed to not actually store allocators. They were allowed to create them whenever necessary and then immediately destroy them, which made this not work. And we didn't really support stateful allocators. And in C++11, this has been fixed. You now have to store an allocator, which is not always free. And I've heard there will be a talk about this on the next time slot. But it gives us the ability to, within the framework of the library, without any language support, we can just do this, and it works. All right, let's quickly go through what StudPMR provides. Oh, sorry. I've run ahead of myself. Allocators do not compose, because allocators deal with types and objects. You cannot easily have an allocator which takes an allocator of an arbitrary type and performs some additional logic on top of that. And Andrei had a very entertaining talk about this a few years back. Stud allocator is to allocation what stud vector is to vexation. There was also something about alligators in the musings about the title of this talk. So if you haven't watched this, you probably should. But memory resources do. Those are interfaces, and they always only operate on chunks of memory that have a specific size and alignment, so we can very easily chain them. And that's the idea behind what we call a memory resource adapter, of which there are a few in StudPMR. Okay, so welcome to C++17, 2 years ago. So we have memory resource, so the virtual base class. We have polymorphic allocator, which essentially amounts to the allocator that you've seen that had a memory resource pointer. There's a few weird caveats about that, but let's not go there. We have two adapters called unsynchronized and synchronized pool resource. We will get back to them. We have an adapter called monotonic buffer resource, which allocates a big chunk of memory from its upstream resource and then holds a pointer to the beginning of that, and when asked for an allocation, just gives you the next chunk of memory from the pointer and moves the pointer forward. It's very simple. It's very easy to misuse. You cannot free memory into a monotonic buffer resource. You have to call the allocate, but it's not going to do anything, so be careful. We have new delete resource, which, by the way, is a function and not a class. We need to work on our naming some more. But it's a function that gives you a pointer to a global instance of a resource that uses operator new and delete to allocate memory. And we have null memory resource, which just does not allocate memory. And we have getSet default resource to set and get a global pointer to a resource that we want to use. And all of the types in PMR that takes a memory resource have a default constructor which defaults to the value of calling getDefaultResource. So this is a way to be able to dynamically change the source of memory that you get in a given part or maybe in your entire program at random places. All right. Everybody good?
Could you give an example when you would use the ability to change the global resource? When do you use that?
Could I give an example when I would change the default resource?
Yeah, well, from where would you change the global resource to something other than the production default resource?
I don't know. I don't actually use them. I can imagine, like the one use case that I can imagine is building a system that doesn't want to propagate a resource along all the call chains and just decides to use the default resources. and set it up at the front of main. And I don't.
tried that 18 years ago at my company.
Yeah.
They died. It's like a global variable.
Yeah. So the comment was do not. Yeah. And the comment.
Use it for testing.
Yeah. The comment is use it for testing, not in production. And the comment is most probably right. If you are going to, so the comment was you could use this for rendering different frames and have different frames use different resources. I would be very scary of you doing that because you never know which resource you are going to use at a given place. And you get into very weird places where this beautiful thing called POCMA, propagate on container move assignment or propagate on container copy assignment or propagate on swap come into play. And you may end up swapping two containers that you thought would use the same resource and end your program at this point because you were wrong. So do not manipulate global variables like this. All right. Yes?
If I understood correctly, the get default resource returns the new delete resource by default?
I believe so, yes. The get default resource by default returns new delete resource, yes. All right, let's try to go lightning fast for this because we are trying to talk about applying all this in case of heterogeneous systems and some more systems than just that. But we have to understand what we are actually talking about. So we need to have a good understanding of what a computer is. And some of these may be not quite what you expect, but let's try to abstract a little bit. Okay, so you have a computer, right? That computer has a CPU, it has memory, and it probably has a GPU. The GPU may be on the CPU because these are confusing times, but you're probably going to have a GPU somewhere. There is some connections between those. The CPU going to memory is going to be faster than the CPU going to the GPU. But this is a very high-level look of how a computer looks like. And by the way, I tried to put like the interconnects, like PCI or the memory bus here, but it went even worse than it's just going to be in a few slides. So let's just remember, everything is connected somehow. All right, so a CPU is not actually like a single thing. There's CPU cores, so there's computational units that execute streams of instructions. A GPU is also not a monolithical thing. There's this thing, at least on our GPUs, there's this thing called an SM, so a streaming multiprocessor, which is defined per architecture pretty much. It doesn't differ much on chips of the same arch. And how many of those you will get will define how powerful your card is. But this is also a lie, right? Because a CPU core is going to have those pesky things called hyperthreads that are going to try to switch between one and the other when there's various sources of latency on the instructions that they are trying to execute. And SM is also not a monolithic thing. And SM is a set of cores, of GPU cores, that are going to use a hardware scheduler to execute as many threads as possible to minimize the various latencies that may be introduced by some of the instructions. What is the big thing that we are missing in this diagram?
The memory hierarchy.
Yes, a memory hierarchy. So the memory is not actually just a blob of memory. It's some number of pieces of hardware that have chips on them. But this is not the interesting part, right? On the CPU, every core is going to have some amount of cache that's local to the core that is very fast to access. the CPU will have some last level of cache that is slower to access than the per core bits of memory, but it's also going to be much faster to access than global memory. Similarly, though, on the GPU, you are going to have memory, and it would not fit on those slides, but the cores on the GPU also have cache, and the SMs have cache. So there is also a hierarchy of caches and memories on the GPU, very similar to what you see on the left side of the screen for the CPU and for the global memory. So there is one, yes? I was about to ask a question, what is the next thing that we are missing? But I've been run in front of, because NUMA was the answer. This is an approximation of something that is called a DGX2. The number of cores is wrong, and of course the number of SMs on the GPU is wrong. But the rough idea is the same because this machine has 8 GPUs on each NUMA domain. So since we have multiple CPU sockets, we will have multiple memory controllers. Some memory is going to be attached directly to CPU 1. Some memory is going to be attached, well, directly in air quotes, to the CPU 1 and 2. Some of the GPUs are going to have a faster path to one of the CPUs than to the other. In a way, you could think of a GPU as its own NUMA domain, because it has its own memory, like at least a dedicated GPU. It has its own memory, it has its own cores, and it has some way to interconnect with the other parts of the system, right? There's more dimensions that we can add to this. On recent network cards, you can enable a mode that I believe is called remote direct memory access, which allows you to put the card into a mode of being like a bridge between remote memory controllers so that you can directly access the memory of a different host, of a different machine over the network. So we have this multidimensional hierarchy of where memory lives and where CPU cores or GPU cores or anything else is. And there is always going to be some cost of accessing memory. Like in your simple desktop, the cost is going to be very simple. There is the cost of accessing cache is this, of accessing global memory is this. But when you start adding those additional components, you have to start thinking about, where is my memory? Is this memory at this address going to be cheaper to access than the memory at this address? Sometimes you are going to just go for a very quick interconnect between CPUs. Sometimes you are going to have to go through the PCIe bus to get between the GPU to the CPU on most systems. There's this beautiful thing called IBM Power 9, which allows you to make this faster. But it's still much slower than accessing your local memory. So we have to think about what memory you are allocating because the costs of accessing different memory are going to be different. And the API you are going to use to access different kinds of memory is going to also be different. Some of this memory you are going to be able to directly dereference, because you have a pointer, which is the star pointer, and you have access to the memory. Sometimes you are going to have to make expensive API calls to actually fetch the memory for you from one place to the other. So the typical definition of a heterogeneous system is a system that has different kinds of processors or cores, right? And for a lot of the problems that we try to solve when talking about heterogeneous systems, we have to take this into account because we have to compile our code twice for different architectures with different tool chains and nonsense like that. But with respect to memory, this does not matter that much. So the problems that we have in heterogeneous systems are also going to show up in homogeneous systems that have those many dimensions of hierarchy of memory. So while this is mostly motivated by heterogeneous systems, specifically systems that are mostly what the first slide was, you have a CPU, you have some CPU memory, and you have a GPU, and you deal with that. But for all the other kinds of hierarchies, the same problems appear and the same solutions, I believe, are useful. Okay, let's go back to what I promised we will talk about. Let's talk about the pool resources in StudPMR. So there's two. The difference is that the unsynchronized one is not safe to access from multiple threads, and the synchronized one is safe to access from multiple threads. Otherwise, they are the same. So the idea is that you're going to allocate memory from the upstream resource. So the pool is going to know about some other memory source that you give it. You allocate it in big chunks because the assumption is allocating the memory from the upstream is expensive. Let's do this as rarely as possible. And then we are going to divide the memory into smaller parts that we are going to allocate to the clients of the pool. We will only allocate more memory when it's necessary, and when our clients give back the memory that the pool gave them, we keep onto the memory, so we don't give it back. And due to how this is, it will most probably use something that I call inline bookkeeping. There's probably terms that people have for this that are different, but let's stick with this one. What this is, we'll get to in a moment. So how do you use this? You can create a default constructed pool. This will default to the default global resource. You can also give it explicitly a specific memory resource to use as a source of memory. You can allocate some memory from the pool. This will most probably invoke the allocate of new delete resource in this case. But when we try to allocate the same kind of an allocation again, we shouldn't need to allocate more memory from new delete because we should have some more. And then we deallocate, it's not returned back. Make sense? Cool. Okay, so what do I mean by inline bookkeeping? All memory comes from a single place, and you are going to keep track of the memory that you own and that you are going to give out together with the actual memory that you are giving out. So it will look something like this in practice. You are going to have some two intrusive linked lists, or actually more, but let's stick with two. You're going to have the list of the big blobs of memory that you've allocated from the upstream, because eventually you have to give it back when you die or when somebody tells you to. And then you have a list of free allocations that exist inside your pool of memory. And you give those out. So to keep track of these free allocations and keep track of this list, because we cannot make more allocations from upstream because that would go counter to trying to make less calls to allocate of upstream. You are going to keep the metadata and the suballocations together. What I did was actually keep them at the back to help with alignment, but it doesn't really matter that much. So they are going to be interleaved, and the pointers that constitute the linked list of free memory are going to be inside this metadata, somewhere between the individual suballocations that you give to users. Make sense? Yes?
What does this metadata typically have?
A pointer. So to go into slightly more detail, and I'm going to look at the clock, you are going to have buckets of different sizes, so you always know what the size of a thing is from the size that the user requested. You always know into which bucket you fall into. So you mostly only need to know where the next free block is. You can do more, of course. You can do like debugging, tracking of this is allocated, this isn't, to do like sanity checking and whatnot. But I believe that the implementation I did for Thrust is just a pointer to the next one. Make sense? Cool. Let's try to go at light speed. Okay, so heterogeneous systems without unified addressing. What do I mean by unified addressing? There is this thing called a virtual address space. This is the view of memory that you see when you tell the CPU to dereference a pointer. And there is some backing physical memory behind that, but we don't care about the addressing of that. When you have unified addressing across multiple different kinds of cores, that means that for at least a subset of memory, you are going to, under the same address, you are going to have the same logical page of memory, the same logical fragment of memory. And it's usually going to be automatically transferred between, say, the CPU and the GPU when it is accessed from the place where it currently isn't. There is always one place where the chunk of memory is. It may be on the GPU, it may be on the CPU, it may be in swap, because that's essentially the same idea. You have a chunk of memory that is somewhere, but not necessarily in the main CPU memory. Let's say we do not have unified addressing, so we cannot just, on the host, dereference the pointer to some memory on the GPU. Okay, so let's try to construct a very quick CUDA Malloc resource. CUDA Malloc is an API that allocates memory on our GPUs. It's a very expensive call to make because it has to synchronize with a lot of places in the driver, because it not only sets up the virtual addressing on the GPU, it also allocates physical memory for it. So it has to synchronize with many things, and it actually commits the memory. So you cannot over-commit on the GPU with CUDA Malloc. One of the primary comments that we in the Thrust team get from our performance team is, could you please call CUDA Malloc less frequently? So let's have a memory resource and have a pool on top of that. And this is where we started, going down the way that we arrive on at the end. So we have the do allocate that we override from the std_pmr memory resource. If the alignment requested is higher than 256, which is throw bad alloc, because we cannot handle that because we only ever give you the alignment of 256. Then we try to call CUDA Malloc. If we get something else than success, then we just throw bad alloc. You shouldn't just throw bad alloc like this. You should throw some exception that actually preserves the return value from CUDA Malloc. Because fun fact, every call to CUDA APIs can give you any return status, because most of our operations are asynchronous. So any call into our APIs can give you any error from any of the previous operations that we've launched. Did we lose audio? So I'm bound to the desk now. All right. So again, any call to any of our APIs can give you any error. So you probably should preserve that and not just throw bad alloc. But anyway. And then we just return the memory that we've allocated. Simple enough, right? When we do deallocate, we just try to free the memory. If we get something other than CUDA success, we throw bad alloc. By the way, deallocate is specified as throws nothing, which means that it's not supposed to throw exceptions. However, our deallocation can fail. So we've made the executive decision to actually throw from deallocate, because that seemed to make the most sense. All right, so let's try to use this. We will create a resource. We will create a pool that is initialized with this resource. We try to allocate memory, and this explodes. So we allocate. So the pool is going to allocate some amount of memory from CUDA Malloc, and then it's going to try to access that memory to store some metadata about the this one big chunk of allocation. This is the place where it will fail, because it cannot access GPU-only memory on the CPU. At best, this is going to segfault. At worst, it's not. All right, so this explodes in one way or the other. Okay, so let's assume that we have unified addressing. So we have some way of allocating memory on the GPU where we get a pointer that is usable both on the GPU or the device or on the CPU or the host. I may go back and forth between those because that's how we usually speak. Okay, so we do allocate. We can throw when the alignment is too big. Now, instead of calling CUDA Malloc, we call CUDA Malloc managed, which is a nicer call. It synchronizes with less amount of state in the driver, so it's much faster. It doesn't actually commit memory, so using CUDA Malloc, you can overcommit your GPU and have a data set that is larger than the amount of memory you have on the GPU and store the rest in the main memory. And again, the same story, we just call CUDA free because that's the same thing. Okay, so we create this Malloc managed resource, and we try to create a pool out of this, and we allocate, and this works. Well, yes, but actually no, because the metadata for the suballocations is interleaved with the suballocations. All of this is, both the metadata and the suballocations are probably going to be smaller than a single virtual memory page, which is usually 4 kilobytes. So if we allocate some of this memory, launch a kernel on the GPU that will make use of that memory, and then we try to suballocate the memory again on the CPU, the pages of memory are going to go back and forth between the host and the device over PCIe with all the latencies and general hurt that this involves. It's still faster than CUDA memcopy, I've heard. Yes, I see your surprised face. That's what our performance people told us. But it's still going to be awful unless you allocate all the memory up front and never touch the pool again until you've done all your work. This is not a good solution, and this would not work for us because the use case we had was that we had one global pool that we used to avoid calling it CUDA Malloc all over again. We wouldn't be creating small pools for specific tasks. Like sometimes we would, but not in the general case, and this would not solve it. Okay, so let's go to what Thrust MR is. We also have the equivalents of the standard pool resources. We have more tuning parameters because if any of you have ever looked at the pool options in StudPMR, they are not great. They have like max chunk size and something else. They do not have min chunk size, so we cannot say allocate only chunks that are greater than this. They do not have a way to tune the sizes of the actual buckets of the pool. StudPMR pool options doesn't have a way to specify the alignment required for suballocations. And whenever a pool resource encounters a request for memory that is aligned more than its internal alignment, it's just going to go to the upstream. So this is miserable. But we also support fancy pointers, and this goes back to the point I made on that slide with the quote from the interview with Alex Stepanov. We have pointers that do magic. So our memory resource is slightly different, and this is not actually how it looks like, but the code is ugly because it's CUDA and there is a lot of annotations and whatnot. But the idea is, our memory resource is actually a template. The template parameter of the base class is the kind of a pointer that we operate on, which often is going to be Voidstar, but sometimes it's going to be like Thrust CUDA pointer or Thrust device pointer, depending on where in our stack of allocations you are. This part of the slide is missing one thing. There is a specialization for Voidstar, which derives from CppCon memory resource. So if you are operating on pointers that are just raw pointers, this operates with the standard facility, which is great. But often we do not use Voidstar. So again, allocate is going to look pretty much exactly as previously, only instead of the Voidstar, you're going to have a pointer. And deallocate is going to look mostly the same again. There's also the is equal, but I'm going to skip over that because that is awful. Make sense so far? All right, so the actual memory resource that provides us memory from CUDA Malloc looks something like this. We have a resource that derives from the memory resource for CUDA pointers to void. And then we have doAllocate, which is, again, going to do mostly the same as previously. And we have doDeallocate, which is, again, going to do mostly the same thing. Seems reasonable? Okay, so there is a magic thing about Thrust pointers. The references they give you aren't actually references, those are classes. But those classes know how to automatically transfer your memory from one place to the other. So if you have a Thrust pointer to Thrust pointer of the CUDA system to something on the GPU, if you dereference that, we are going to automatically call CUDA memcopy to get the memory, to get the state of the memory onto the CPU, and when you are done, we are going to CUDA memcopy back. So we can have a CUDA device memory resource, CUDA Malloc, and we could do an unsynchronized pool resource of this CUDA Malloc resource. This, by the way, is a template, but see that I'm not a huge fan of this language feature, but this is one of the places where it's really nice because I don't have to say anything. I just write code as if this was CppCon. And then I can allocate from this pool. I will get a CUDA pointer to void that I can just use then. So it's great, right? Well, yes, but actually no. We are back to the same problem we had with managed memory, because we are still having transfers between one place and the other. Except now we are just doing CUDA memcopy instead of the silent transfers that managed memory gave us. It's similarly not great, and supposedly CUDA Malloc is slower. I think it has something to do with like having to send more messages over PCI to synchronize some states before you return from CUDA memcopy. There's some nonsense there. Okay, so clearly storing the metadata inside the same allocation as the suballocations is not a great solution for when you have memory that may migrate between different places in your system. Enter something that I call bookkeeping on the side, and this is where the word bookkeeping came from in my mental model of this, because I wrote a template that had a template parameter. I didn't know how to name it. I just said bookkeeper, and that seemed fine. So the memory from suballocations is going to be allocated separately from the memory used to track the suballocations. That's the basic idea. So you will still have some upstream resource that will give you chunks of memory that you then subdivide and give out to users. But you will also have some other resource which will provide you memory from the actual metadata of the chunks and of the free pieces of memory that you have. Now, you could also do this, but I don't know how useful that is. So this is inherently going to use more memory, because the structures are larger. There is less intrusive lists, and there is more lists in general. The one case where I can think this may be useful, like using this strategy with the same resource for both the metadata and the suballocations, is when you're doing something that is extremely careful about caches and fills a cache miss due to a cache line being stolen by a different CPU in a manner that is not acceptable. But I don't have use cases like that. So as I said, this may be useful because the memory may be in the same place, but you don't want to steal the cache lines. But in our case, we just want to do this. So our bookkeeper resource is just going to be a poor, plain, old, new delete resource. We are just going to allocate host memory for this because we don't care about anything else. But the upstream resource is going to be a CUDA Malloc resource or CUDA Malloc managed resource. And we no longer clash and no longer fight for the same pages of virtual memory. And it's great. So the name I've chosen, and I admit I may not be the greatest at naming, is a disjoint pool resource. And again, synchronized or unsynchronized. If you have better name ideas for this, I'm all ears, but maybe after the talk. So we, again, create the same device memory resource as previously. You create some new delete resource. In our case, this is a class and not a function. And you just create a disjoint unsynchronized pool resource that is going to do all the right things. And you give it two resources to deal with, one to allocate metadata, the other to allocate the actual memory. And again, this is a template, but see that happens to sometimes be useful. And this is actually yay, because this actually works nicely. We don't fight over memory. And as I said, I believe that this approach is useful not only just for heterogeneous systems, but obviously heterogeneous systems is where the fancy pointer support comes in. But if you have multiple NUMA domains, or maybe multiple hosts that are directly connected over the network to access each other's memory, you may also want to do this because you may want not to have to pay the cost for accessing the metadata when it's perfectly fine to be local. And that's the gist of that talk. If you have any questions, there's a microphone. If you don't, I have some bonus slides. It's your choice.
First, thanks for the talk. It was really great. I have a question. So how do you deal with a case where you have multiple GPU? Because as far as I know, if you want to do memory allocation across multiple GPU, you have to set different devices, which lots of time can become a mess.
So in practice, in practice, we have a way to query a global resource of a given type. The question was, how do we deal with memory allocation when we have multiple GPUs, and presumably with caching? Yeah, so we generally use this Thrust API that we call get per device resource of a given type. It's a template. You can tell exactly what kind of a resource for the current device you want, and we will save that somewhere, and we will manage the allocations separately for different devices. I believe that for managed memory, it's not as much of a problem. But the APIs for memory allocation on CUDA are not great. So yeah, the general strategy is to have some set of resources that are specific to devices.
Hey, thanks for the interesting talk. I've noticed that obviously your trust allocators are actually templatized. Am I correct in saying that from the PMR model, you are getting the benefit of the separation of concerns between construction and allocation, but not really the benefit of having this type which
I have bonus slides.
Okay, I can wait if that's the case.
Can we go to the bonus slides? Because
can.
Vittorio is asking about the trade-offs between having this all templatized versus using dynamic polymorphism everywhere. And I have bonus slides. And I think this gets at what you were asking about. So this is a frequent question, right? Do we design our API in a way that will always be dynamically polymorphic? So we'll always do the virtual dispatch, and we will always have those reference semantics, or we'll have to build those value type wrappers on top of them to actually have copy and value semantics. Or what do we do? How do we structure our APIs to deal with this? So here's a difference of how StudPMR and ThrustMR actually deal with upstream resources. In case of StudPMR, nothing of this is a template. This all just takes a pointer to a memory resource. In case of our resources, because we do not care so much about the polymorphic aspect of this, like that was not the goal we've started on. We use templates everywhere, and most of our resources are actually final. And in most places, we actually do allocate and do deallocate directly, because that is very easily devirtualized, and our experiments have shown that compilers aren't that good at doing devirtualization that is behind a member function call. For some reason, I do not understand why, because those should be trivially inlineable and should be equivalent. But so we just always keep the information about what the actual upstream resource is, as far as our user tells us. Because you can still have a memory resource that comes from somewhere. You don't know what this is. And you can still create an unsynchronized pool resource that is going to do virtual dispatch, right? So we did not lose anything, except maybe the syntax and a few other things that will appear on the next slide. But we still end up being able to represent the same idea as StudPMR. We are still able to have actually polymorphic resources and adapters, despite the fact that generally we have everything templated. And the trade-offs are these. When dynamic polymorphism is default, you have less code to generate because you don't have to instantiate a whole bunch of templates. The code is going to be simpler because there is going to be less templates. And we can move the code out of headers because there is going to be less templates. But you're always going to pay the cost of a virtual call, save maybe for some rare cases where the compiler is able to inline through a possibly huge amount of stacked adapters that implement different policies. So you would have to count on the compiler. When you make it opt-in, like in our case, because we still have virtual functions, we just don't use them as virtual functions. We make less virtual calls. We are easier to inline because you don't have to devirtualize a bunch of calls. And we are still able to fall back to the virtual dispatch at runtime if necessary. All of our code is templates. But since our library is templates, pretty much nothing else, we don't really care because our compile times aren't that great anyway. So it's all good. So my general recommendation, unless you have good reasons for doing otherwise, is if you want to be composable, try to make your thing composable at compile time as well. Because it's not hard to still be able to have virtual dispatch and runtime polymorphism and be able to preserve all the type information at compile time when it's useful and reasonable. And that's all I have. Thank you.